So now we introduce more general concept of list coloring. And this concept will be useful for us to prove Brooks theorem, which we previously mentioned that this inequality holds, but if we can characterize the equality case. So we will show that this equality holds only if G is something. That means, we get a better inequality if G is not one of them. So this theorem is called Brooks theorem. And we will, prove this. And then in order to prove this list coloring is a useful concept. And as well as, this list coloring is also a very general concept, which is more general than just proper coloring. So we will learn this. So again, we are talking about this proper coloring when there is some graph and then we want to color the its vertices with certain color so that all the adjacent vertices get different color. And there are many situations. These vertices could represent lots of other things. And this color also could have many meanings, depending on what problem you are working on. And that can be captured by this graph theory problem. And in some cases, we are assigning colors to each vertex. And now we are assuming that at every vertex, same set of colors are available. But this might not be the case. For example, if the vertices are stations and you are assigning colors as a frequency channel, at certain location, some frequency channels are not available, and some location, some other frequency channel might be available. It could be all different. For example, these are all stations, but somehow, there are some other station that you have no control of it here, and then it's already using certain frequency channel. And that affects, so these are nearby. Here you have no control. So this is like, the satellite station for other company so that you have no control. It's already using some channel. So if we use the same channel on these vertices, it will introduce jamming or noises. So that channel, that specific frequency channel is not available here, but it's available here because these are far from here. That could be possible, or there are many situations you can come up with. These vertices could be cities, and colors could be some resources that you choose, and then some resources might not be available at certain city. Some resources might be available, and there are many other situations that you can think of. So this introduced the following concept. So when you have a graph G, we say that a list assignment L is a function defined on the vertex set of G such that the L of B is a set of colors which are acceptable for this B. So this vertex there are like some available color, and that's L of B. And we say that on L coloring, what is L coloring? This L coloring is proper coloring. It has to be proper coloring. So all the adjacent vertices should get different color. f of g such that its value is chosen from the list available at the vertex. And we say that a graph G is K, either K choosable in the way that you are choosing your color from this list. Or we say that list K colorable. Or we say that, if it has an L coloring whenever the list at every vertex has either list K or all vertex P. And we define the concept corresponding to the chromatic number, which is least chromatic number. Or it's also called choice number. Or it's also called choosability. And then write as KAIST of L of G. I mean, sometimes people should use CH of G as a choosability or choice number. But, I mean, let's use KAIST of L. This is the minimum K such that this G is K choosable. So we define this new parameter, least chromatic number. And okay, now we have defined this least chromatic number. And what's its relationship with the chromatic number? One obvious thing is that the chromatic number is at most least chromatic number. This is actually a generalization of the chromatic number, the generalization of the proper coloring. Proper coloring is the case that every vertex has the same list of colors which are available at that vertex. Here, in this list coloring, you can potentially have different lists. This is more general case. Here, even in the case where all the lists are same, you should be able to finish the coloring, which is the setup for the proper coloring. So this is more general case. So that this inequality holds. It's easy to see that this inequality holds. However, again, this gap could be large. This gap can be arbitrarily large. So let's consider one example. Consider a complete graph KMM, where we choose this M as 2K minus 1 choose K. Then what's its chromatic number? Chromatic number is 2. This is complete bipartite graph. Right? Okay. Then what's its least chromatic number? So we want to show that its least chromatic number is at least something. Then what do we have to do? We have these vertices, and we assign some list on these vertices. And we show that there are no L coloring. So you cannot choose each color from the list so that you obtain proper coloring. If that's not possible, that means that provides a lower bound on your list chromatic number, because this list provides that this is a list that you cannot complete. That means the maximum size of this list, minimum size of this list provide the lower bound on the chromatic number, list chromatic number. So what's your list? So for each partite set or part, so this set are called partite set or part. This part. Anyway, for each partite set, we assign, say, each K set of size K in bracket 2K minus 1 to each vertex. So for example, when K is 2, maybe let's make it a bit more complicated. When K is 3, then what do you assign? In each vertex, 3 is made too big. Let's make it 2. Go. You have 3 vertices. Here you give the list 1, 2. Here you give list 2, 3. Here, 1, 3. And here you give the list 2, 3. 1, 2, 1, 3, 2, 3. And you have all possible 9 edges. So, then what happens? If F is a proper L coloring, then what happens? It's a proper coloring from the list. And this is complete bipartite graph. So each color is used on only one part. So if color 1 is here, color 1 is here, then it's not proper. If color 1 is here, used in here, then it's never used here. Then what happens? Then by pigeonhole, there are 2K minus 1 colors, and they are used in almost one part. That means there is one part using at most K minus 1 color. Because 2K minus 1, no matter how you partition it, one part has size at most K minus 1. Then let's say this is the part. Then this part, then the complement of this K minus 1 color, some K color in this bracket 2K minus 1 are not used on the vertices of, let's say this is X, one part X. But something is weird, right? On this X, what have we done? We give the list on each vertex set so that the all K set in this 2K minus 1, bracket 2K minus 1 is appeared. However, how we assign this list, some vertex in X as exactly this K set as the list. Okay? But what does it mean? So all those these K colors are not used on X. But at this vertex, those K colors are the only available colors. Hence, it is uncolored. A contradiction. So, I mean, there are no L coloring for this assignment. So, this is not K colorable. So, this complete graph has least chromatic number bigger than 3, bigger than K. So this shows that this least chromatic number has very different behavior from the chromatic number. Okay. However, I mean, the very basic bound on chromatic number extends to the least chromatic number. One of them is the greedy coloring. This works for least coloring. So what it was, you choose vertex one by one, and then you give the color which are least index color among the available one. And you keep do that. And then at some point you have a vertex, and then out of all available one, you choose the one that, I mean, that's available with the delta plus 1 color. If the number of colors is at least the maximum degree plus 1, and every point, it doesn't matter which color are available at this vertex, as long as there are delta plus 1 available color, then earlier neighbors may have used up and most delta of them, so 1 remains. So you know that its least chromatic number is also bounded by the maximum degree plus 1. And also, because you have a chromatic number and least chromatic number, then you know that this is exactly delta plus 1, or G is, say, K delta plus 1, or C2K, whole cycle or complete graph. So that means equality holds everywhere here. So this are all equality for this graph. In fact, we can prove the following theorem. Which is called the least extension of the Brooks theorem. Says that if a connected graph G is not a complete graph or whole cycle, then its least chromatic number is at most maximum degree. So that shows that the equality here holds only for these two classes of graph. And also equality here holds only for these two. This is called the least extension of Brooks theorem, because Brooks theorem is the case where you have a chromatic number instead of a least chromatic number. That's called Brooks theorem. This is the least coloring version of it. So we want to prove this. In order to prove this, if I just give you some idea on why why this coloring is useful to deal with this kind of problem, is that if you have a graph, and then assuming that you want to show that its chromatic number is at least something. So let's say K. the K many colors are available. And you partition your graph into some part. So this is like a subgraph, H of G, then it's G minus the left. Somehow you color outside somehow, and then now you want to color inside. This is colored. This is not yet. But assuming you already have color, now what? For each vertex, which is adjacent to these three, now these three colors are not available here. But for other vertex, let's say this one color is not available here. So once we have completed coloring here, now on each vertex, you have a different list of acceptable colors. This different list of available colors. So once you have some coloring here, now you want to extend it. And that's same as a list coloring problem on this graph. So in such a sense, list coloring is more flexible when you are applying some proof, when you want to prove certain coloring problem. It allows you to deal with the problem piece by piece. And while you're doing that, when you are dealing with one piece, you can actually get use the information on the previous piece, how you color those, and then that puts some restriction on the current piece. So that's why it's useful. In terms of that, let's define some concept and then collect some basic property of it, which will be useful for us to prove this list extender of Brooks theorem. We define that the graph to be degree choosable if it is L colorable whenever its list at vertex B has size at least its degree. One more thing about this coloring being more general than proper coloring is that for different vertices, it might have different size of list. For proper coloring, every vertex you have the common available color, which has all same color. But here you might have different size of the list for different vertices. So this definition makes sense. Each vertex you have at least the size list of size at least its degree, then you can finish the coloring. Then you say that this is degree choosable. And what graphs are degree choosable? We can find some easy cases which are degree choosable. If you have a connected graph G, and then let L be a list assignment such that at each vertex its list size is at least degree for all vertices B. Then what conditions are useful for us? If at least one of them has a strictly bigger size for some vertex Y, then C is L colorable. So if some list has size one bigger than it, then we can complete the L coloring. And another is if B is a two connected graph, and the two lists differ So there are two vertex which have different lists. Then she is a color. These two will be useful. So let's prove first one. If we have one vertex which is bigger, then we can prove that this is L color. So if we come back to the greedy coloring algorithm, every time you color the vertices, and if this we know, then when do we get the problem? We might be stuck at some vertex if all the available colors are used up. That means for this vertex, all its neighbors should be earlier neighbor. If one of them is actually later neighbor, then it has at most degree minus one earlier neighbor. Then there are one color available. In that case, we are not stuck. So the bad case is when some vertex has all the earlier neighbor, but it's one vertex, it has strictly bigger size. For this, it's okay. Even if every vertex, every neighbor is earlier neighbor, this is okay. Then, what? It's natural that we want to put this at last vertex in this ordering. You want to take a certain vertex ordering so that all the vertices, it has at least one later neighbor, so that the number of earlier neighbor is at most degree minus one. But there is one vertex which is not possible, which is the last vertex. You want to put y in there, then, and or the other one, you want to make sure that it has one later neighbor. Which is possible. How? You take a spanning tree. And you consider this as the spanning tree rooted at y. What does it mean is that you have this and then you specify y as the root. It's nothing but just a tree with the one vertex label. And what you do is that in here, you know that it has at least two leaves. And you choose the one which is not y. And you move it to the this is B1. You move it to the here at the beginning. And you see the remaining one. And you choose the leaf which is not y. And you move it to B2 and so on. This is B3, this is B4. Until you have a Bn minus 1, and then the last one, y, is the Bn. Then what do we know? Since every time this Bi is a leaf on this spanning tree, on this vertex, that means it's sending at least one later neighbor. So in here, every vertex Bi with I being n as one later neighbor. So we choose colors gradingly with respect to this ordering. Then what happens? Every vertex B has less than its degree earlier neighbor, so you can choose a color for it from its list. So, if the vertex is not the last one, but the last one, you have a degree list bigger than its degree, so you can complete. I will not write it in detail, but it proves it. A. And let's prove the second one, B. So what do we know? We know that we assume that the lists are not identical we know that two vertices have different lists. What do you know? Since G is connected, we can take these two vertices have different lists, so you can take a path between them. Along a path between them, we can find two adjacent vertices x, y, such that L of x and L of y are different. So that let's say L of x minus L of y is not empty. Why? We know that this vertex and this vertex are different lists. And we see this vertex. If this has we see whether this and this have the same list. If not, then this is your xy. If they have the same vertex, same list, then we take this path. So they have a different list. Now you check this vertex. If these two have the different list, then this is your x and y. Otherwise, you cut this out. And because this and this have the same list, so you have this path. You keep move on. And at some point, it might, collide. So all of these have the same list, all of these have the same list, and this is what you wanted. And once you have two adjacent vertices with different lists, then one must have an element that the other doesn't have. That one is your x, and then the other one is y. So let's say C is the one which is in x, but not in y. So now what do we do? You have this graph, and then you have x, you have y. Now what we do is we define a list L prime on all the vertices other than x by L prime v is either LV or LV minus C. This is for the non-neighbor of x, and this is for the neighbor of x. Basically, what we are doing is that we give the color C here, and then we forget this, and then we shift it. Because this is colored by C, we kick out C from all its lists. However, what do we know? Y doesn't contain C. That means other vertex, the list size is decreased, but Y doesn't. Then what? We have the size of L prime of V is at least the degree of V in G minus X. So you consider this subgraph of G, which is obtained by deleting this X. For all V in this G minus X, this holds, and furthermore, this specific Y, you have this. But moreover, what do we know? As G is two connected, this G minus X is connected. So we have a connected graph which is degree choosable, not degree choosable. This L prime satisfies this condition, and then this Y satisfies this condition. So we can apply A. And A is that there exists an L prime coloring of G minus X, and this extends by coloring X by C to an L coloring of G by using color C on X. So this provides some lemma, and using this property, we can, these two properties will be useful for us to prove this least extension of group theorem. And also, so using that, we can prove this theorem, which is also useful for proving certain graph with degree choosable. If a connected graph G has a degree choosable in this subgraph H, then G is degree choosable. So we can prove this. So basically, how do we prove this? You have this in this subgraph H. And in G, if you take out H, then you have the connected component. So G is connected. Let's say, and you are given with the list L. Now what? You delete this, and then you see this. Now each vertex here, there is at least one vertex sending edge to here, at least one vertex sending edge to here. And this L satisfies that L of B is at least size of degree of B for all B. But now what happens for these vertices? This vertex sends out some edge. That means inside of this component, it has vertex degree lower than before, because it's sending one edge out and then which is disappear. This is sending one edge and which is disappear. Then by using the A of the previous lemma, you can finish the L coloring here and L coloring here, L coloring here. And then you can, once all of these are colored, this color, so if this is colored by red, then you kick out red from here. If this is colored by blue, you kick out blue from this list. And then what do you have? You see this inside of this H. Now some vertices lost the degree, but its list size also decreased, because this is no longer, red is no longer available here, blue is no longer available here. So after deleting the color from the list and then lowering the degree, the condition that the L of H of B is at least the degree of B in H is satisfied. And H is degree choosable, so you can finish the coloring. So that's the, proof. And maybe let me write it. So let L be a list assignment for G, with the list size being at least its degree for all vertex P. And you consider each component F of G minus the vertex of P is as a vertex with the label in pH, since G is connected. So that means what? That is, if we use the same list as in G, we have a vertex V with its degree in F its list size is strictly bigger than, and maybe let's use Y here, bigger than its degree. And by A of the previous lemma, T minus BH, each component of it has a L color. So this has an L coloring F. Now we form our list assignment L prime for H by deleting from its list all the color used by F on neighbors of P. And what? Then we lose at most one color for each neighbor, which is not in H. Then what? Since the list size has at least the size of, degree of being in G, we now have that the list size of L prime B is at least the size of, at least the degree of B in H for all the vertices. And you use the degree suitability of H. H now has an L prime coloring F prime. Then together F and F prime form an L coloring of G. So this proves this. So then what? And this lemma shows that if you want to show certain graph is degree choosable, then all we have to do is to find the degree choosable induced subgraph. So that provides certain tool for us to prove this least extension of Brooks theorem. And next is that then what graph are degree choosable? If we prove certain graph is degree choosable, and if we find this graph in the larger graph, then this is also degree choosable. So we will we need to collect one more lemma showing that certain simple graph is degree choosable. And then in order to prove G is the degree choosable, we show that the G contains this graph with some simple structure as an induced subgraph. So in the next video, we will prove that and then collect tools, and then we will prove the least extent of Brooks theorem. Okay, then I will see you in the next video.